So thanks everybody for joining us. Super excited for today's webinar. We've had a couple of webinars in the past focusing on using Airflow for machine learning use cases, which is a topic we're super excited about internally. There's lots of cool work going on in this area, both at Astronomer and in the community. So happy to share a specific use case today. Just a bit of housekeeping before we get started. Assuming that the chat is not working for everybody right now, please feel free to throw any of your questions in the Q&A feature within Zoom. We will save some time at the end to answer those. So throw those in there as we go through. We will be recording this webinar, and for anybody who registered, you will receive the recording as well as any materials that we go through today afterwards. So no worries there. And I think that is it for housekeeping. So with that, I'm going to go ahead and hand it over to my colleague, Jeff Fletcher, who's over in Europe. It's late for him. We're very happy for him joining outside of working hours today to talk through this super exciting use case. So Jeff, go ahead and take it away.
Cool. All righty. Thank you very much, Kenton. So my name is Jeff Fletcher. I'm the Director of Field Engineering for Europe. I'm based about 100 kilometers south of Amsterdam, which is what everyone knows in the Netherlands. And today we're going to talk about doing MLops, or machine learning operations with Airflow. I know that the previous webinar looked at doing MLops with Airflow a lot more broadly, but today we're going to go dive in a little bit deeper and focus on an actual use case doing image classification with Tensorflow and MLFlow. This is a lot more hands-on and kind of a little bit more in-depth technically. So feel free to ask questions and let's see how it goes. Okay, so where am I? The screen. The first thing though that I want to do is just talk about what we mean when we talk about good machine learning operations. So machine learning operations as a sort of general topic is something that I think is focused a little bit too heavily on from a lot of the academic research that comes into this. And a lot of machine learning is put forward by people who are coming from pushing forward technology and pushing academia. And in a business context where I think a lot of where we would be from, machine learning needs to be something that solves a very specific business need. The business will have a requirement, and machine learning can predict around an area that they don't know. So if you have a bunch of customers that might be churning and you want to know which ones are churning, that is the business need. And the ability to be able to make that prediction reasonably accurately is one side of machine learning operations, or machine learning. The other side, though, is the operations side, which is keeping something like that running. This needs to be available on a continuous basis. And this is what we're focusing on for this particular presentation is how do you continue to solve that business need? How do you make sure that your machine learning application is valuable and continues to be valuable? I need to find my, there it is. I have something on this monitor. Okay, so when we look at a standard end-to-end machine learning pipeline, this is a reasonably good view and workflow of what most machine learning pipelines look like, which is a business requirement comes in from a team of people that want to know how do I identify which of our customers are churning. You as the data scientist would then have a look at, get some data from data engineering to see what is available, do the data exploration, so understand what information exists inside this data and if it can help answer that question, extract features from that data so that it can go into the model, build the model itself, and then pass that on to a machine learning operations function, which takes that model and puts it into production. So the model is now deployed and it's operational and it's delivering value. That model needs to be monitored because the environment changes and the data changes. And if there's a big enough change, you trigger a retraining process. These end-to-end steps can be managed by a lot of different types of tooling. So I've seen everything running from people doing this purely with Python code they've written themselves, to Jupyter notebooks, to specific things like VeloHigh or CometML or ClearML, Airflow is in the mix, VS Code, et cetera, et cetera. There's lots of different ways that these type of machine learning pipelines can be implemented. But in order to maintain and continuously keep these things in production, we want to look at the components of this that are automatable. And by that, we need to take out what people do. And in the data science context, exploring the data and coming up with the initial model is primarily the job of a data scientist. Their function is to understand if the data represents a way to get to that answer, and then come up with the initial model build. So is this a classifier problem? Is it a regression problem? Is it an NLP problem? What format of that model and input and output, what does that need to look like in order for that to work? The rest around that can be automated. Data ingest can be automated, feature extraction, model training, model deployment, model monitoring. And if we take that workflow down, we can trim it down to a standard machine learning workflow that is ingest data, extract features, train the model, deploy the model, and monitor it end to end. And it's with that in mind that I want to talk about how we can do this with Apache Airflow. So with Airflow, automating these different processes, the first question would be, why would you use Airflow? So Airflow is Python native, which means that in the data science world where Python seems to have won, this would be the standard language for both your data scientists and your machine learning engineers. It is a common interface and used by a lot of different teams already, so people understand Airflow. It has a massive amount of integration. If you just look at the sheer number of operators that are available for Airflow, it can talk to so many disparate systems, so it makes sense in that context. It can be actively monitoring and alerting, so if something goes wrong, you can be told about it. It's open source, so you can extend it, you can build onto it. It's pluggable, so it can fit into a lot of different places. It does not care about the data itself. And this is an important abstraction, and we'll get to this when I talk a little bit later about some of the tooling, specifically things like Kubeflow. This does not Airflow does not need to know about the data itself. It needs to know about the processes that are happening, and it runs perfectly well in the cloud. So you can take that standard workflow and you can automate each of those bits and pieces with Apache Airflow. And that's what we're going to do today. We're going to tackle a specific machine learning problem, and we're going to use Airflow to automate the components of a complete end-to-end life cycle. So let's start with this particular project. How this project came about, the actual genesis for me was I was a year and 3 months ago. I was in hospital with quite severe COVID, and I had pneumonia. And I was talking to the radiologist and the pulmonologist, who I think is a lung person, could be a cardiologist, but I'm going with pulmonologist, I'm not sure. And they said, looking at the picture of my lungs, they can see that I have pneumonia, but they're not sure if I have a bacterial infection or a viral infection. So they needed to send it off for blood, and blood work takes an hour. And I was wondering, is it possible to actually use a machine learning algorithm to look at that picture and decide whether I have bacterial or viral pneumonia? Turns out a lot of work has been done in this space, and there's actually a fairly good Kaggle data set that covers this. So for this project, I've taken a lot of that work and I have built on an X-ray class or a image classifier that looks at an X-ray and will determine whether you have pneumonia or whether you have your lungs are normal. The complexity of getting into the 3-class classifier is there, and it is available, and I do talk about it in some of the notebook information, but specifically this is going to try and determine, based on an X-ray image, to classify this as having pneumonia or being normal. I did add into it a Lime image explainer. So this basically tells you what you see in these pictures is these are the dots that the pixels thought that, well, these are the pixels that the machine learning algorithm attributed the highest effect on the outcome. So what is highlighted is the thing that said that this is most likely what determines this to be normal, and these highlights are most likely what determines this to be pneumonia. So this is all inside this repo, which I'm going to paste into the chat now. There we go. So this is the repo that I'm working with from this. This uses and is quite well documented. So there's a README that kind of talks you through how you can build all of these processes out. But we're going to go ahead and build this end-to-end implementation. And the end result that we're going to get to is we're going to have an application that's running that can make a prediction for a new image. So if I go here, there's a Streamlit application that comes up that can make a prediction for you. So this is the live Streamlit application. So it's currently running, and it chooses a random image. And when I say predict via API, it sends this image off to a Ray server, and we'll get into the detail of all of these and how they're coded and how they're built, but I'm just kind of giving you a high-level overview. which Ray is using Ray serve and creates a REST endpoint, which takes, and Streamlit takes a byte encoded version of this image, sends it to that API. If I go predict via API, that goes to the API, and then it comes back. And it gives me the prediction of normal. Let's grab another random image. Let's do that same prediction. It's being sent to the API. It's coming back as having pneumonia. You can see this is my model number. So this is the model that it's using when it's actually making that inference. And end to end, this is the process. Is we're going to go and grab some new images. We're going to train the model on those new images. We're going to redeploy this model, and we're going to restart all of the applications. And we're going to do all of that using Airflow. So from here, now that I have this running, let's first talk about the infrastructure and architecture that is deployed for this particular implementation. So at a high level, I need a couple of pods running or a couple of services in order to do that. The easiest way for me to do this is I'm going to use Kubernetes. So this is a Kubernetes cluster, and I'll talk in more detail about the architecture, but at its highest level, I have a pod that's running Ray, in particular Ray serve, that I'm using as my REST endpoint for making inference. I have an MLFlow instance that's running for me to track the experiments for model training. I have a Streamlit instance, which is the application that you've seen. And then I need ephemeral pods. I need a pod that will come up to do the model training. I need this pod to have GPU, but GPU is expensive. So I want autoscalers involved, and I need other pods to come up and down to do things like grabbing new data and following all the way through. This all needs to have network access to these services, so both the end user and my Airflow orchestrator can access it. And there needs to be a long-term persistent storage as well, so that when I store images or store models, all the pods will have access to them. So that is at a high level what I'm going to build for the cluster that this runs on. The actual DAG itself goes through several steps. So the starting point is I am checking for new X-ray images to land in a particular S3 bucket. Going to use an async sensor, and I'll talk a little bit more about this as we go as well, but it is something that just makes things a little bit easier with regards to fetching files from an S3 bucket. From there, I'm going to split into two pods, both of them running the Kubernetes pod operator. This first one will fetch those new data from S3 and store it on the local infrastructure. Second one will go and fetch updated code from my GitHub repo for the model training code. Then when that's complete, we hand this over to the next process, which is also the Kubernetes pod operator, but this one has some special attributes to make sure it appears in a Kubernetes or in a node that has GPU attached, and it runs the training code. So the training code is its own particular file that lives on that infrastructure, and it runs for the training. When it's complete, it saves that file out, and we're going to dig into the code as we go, but just sort of at a high level. We go and fetch the updated code for Streamlit, and as well as to point it to the newest model. We update the Ray server, so that the Ray server now uses the newest model as well. And then when it's completed, it sends me an email to say that it's done. So end to end, this is the DAG that we're going to go and build. Now, for the Kubernetes architecture, for that cluster, there's a couple of things that I needed to build. So the first is this is the overall view. Now, in this repo, I have a document in the Kubernetes docs section called EKS cluster, which is a build guide on how I built out this cluster and the various bits and pieces. It's kind of cobbled together from a few things, but if you follow these steps all the way through, you should end up in the correct place, which is a Kubernetes cluster that has two node groups. One node group is my CPU group. This has a minimum of one node and a maximum of 5 for this particular deployment. This is where my main pods run. Then there is a second node group, which is GPU, which has autoscalers and the NVIDIA daemon set. And the NVIDIA daemon set is important so that when you actually send a task, you have to set the resource limits on that task so that it will elect to go and deploy a pod inside a GPU-based node. These are all backed with a persistent volume. In this instance, I use EFS for the persistent volume because it's easier to connect it to other things. And also you can have lots of pods connecting to it at the same time. And then we connect these services, which is the MLflow, Streamlit, and Ray, via load balancers to the network traffic. So in this instance, it's coming over the internet, but I restricted internet access to this specific load balancer from my local laptop. but it creates this cluster. So this is my overall Kubernetes cluster, and this is where my various services are running. I don't yet have Airflow attached to this. So my starting point is I need local development so that I can test various bits and pieces as we go through. So for local development, I'm going to use the Astro CLI. Astro CLI is going to use Docker desktop on my local machine, and it's going to bring up a version of Airflow on my local machine with a couple of pods running Docker that allows me to connect through to that cluster and test how these Airflow processes work from my local development environment. So if we go to here, or where is it? There we go. So from here, I have downloaded the CLI and cloned the repo into this local directory, and I go astro dev init, will initialize it, but I've done this already. Astro dev start will start up the local instance, but now all I need to do is astro dev ps to see that it's running, and you can see that I have those 4 pods running. So those 4 pods, web server, trigger, etc., all running. So I have that there. So my local infrastructure is now set up. Now there are some things that I need to do in this directory before when I start it up so that it is able to connect through to that Kubernetes cluster. So the first thing you'll notice is there's a Docker file that comes with it. I don't know if it's the first thing you'll notice. It's the first thing I want you to notice. So there's a Docker file that's in that directory. And if we go and have a look at the Docker file, you'll see that this uses the runtime image, which is the Astronomer Astro runtime image, which is what we use for deployment into our cloud infrastructure. But it is a complete version of the latest upstream Airflow if you're using 5.06, I think, which is currently Airflow 2.3.3. And that's the base image that gets deployed for Docker and also for Kubernetes when we go into production. Now, in order to connect to that cluster, I have to do 2 things. Because we're using EKS, I need access to a kubeconfig file, and I need access to my AWS credentials. So I need to copy over into the include directory here, my AWS config and credentials file, and my kubeconfig. This lives inside that image. I put it into my git ignore so it doesn't get copied up to GitHub. So this is then secure on my machine. And when we go into production, it means secured in the cloud. But this is the mechanism that Airflow will use to authenticate itself against that Kubernetes cluster. So it needs access to that kubeconfig file. So I specify here, I copy them over into the image. And the other thing I need to do is set environment variables so that the Airflow tasks know how to reach those services. So things that the Airflow tasks need to know is the cluster context. So what Kubernetes cluster are we talking to? The storage path that I've used for the persistent storage, the IP addresses or host names for the Ray server, etc. And this gets passed through. I can pass it through in the UI in Airflow, but it's easier if I do it in the Docker file. So that now when I start up Airflow, all of start up the local Astro instance, all of these environment variables are there, so my processes can work. The next thing that I need to do is I need to say what Python requirements I have, because these processes need to do certain Python tasks. I set them up here. Now you'll see later on, I'm using Tensorflow, I'm using MLFlow, I'm using a lot of things, but Airflow, because Airflow is not touching the data, Airflow is touching the different services that are running up to and including Ray. I need access inside the Python libraries for those specific libraries, but I don't need TensorFlow inside Airflow. You can, but you don't need it because the actual Airflow is running in a Docker image that I use in that Kubernetes cluster when that node spins up. The other thing that you have to include is in your packages.txt file, you need AWS CLI because that's actually used for authentication against it. So when I go astro dev start, after have made those changes, my local instance spins up and I am now connected. I have my DAG. Now my DAG should, in theory, be connected through to that cluster because everything has been set up correctly. So I'm going to trigger this DAG well, actually, no, let me just run through some of the other bits and pieces before we get to the triggering the DAG. There are some things that you need to pass through to the Kubernetes pod operator in order to get this to work. So one of which is that it needs to know the volume mounts. So when it creates the pod, it knows what the volume mounts are for. And these container resources are necessary to pass into the the pod that uses GPU to make sure that it knows to go and request from a GPU, from a node that has GPU accessible to this. So this is what the NVIDIA daemon set does. So the NVIDIA drivers and the NVIDIA daemon sets that come as part of the deployment for a GPU node on EKS includes the ability to understand the number of GPUs on each node. So therefore, it will then go and request in the correct direction. There are some other things that we have to pass on to that Kubernetes pod operator. So specifically, we have to say that it's not in cluster. Airflow is aware of if it is inside its own Kubernetes cluster, it will try and use those automatic configuration settings. If it's not, it will know to then look for other mechanisms to go and authenticate to that Kubernetes cluster. We need to tell it the volume mounts because all of the pods use the same volume mounts. I just pass this in as a set of standard defaults. And when we start to use Kubernetes pod Kubernetes pod operators, then they will all have the same set of configuration details. Now, the first the first task that we run is the S3 async sensor. So it's looking for this S3 bucket. I created an AWS connection. So this is a key and secret, so it knows how to go and read from that S3 bucket. If I go here to that S3 bucket, I'm going to take this file name and I'm going to change it. So object actions, rename object, and we'll call this class underscore temp. So now it's changed. So this file is not accessible now. So if it goes and does an S3 look, that key is not there. And if I trigger the DAG again, you'll see that it goes into deferred state. And because this is a deferrable operator, it doesn't actually take up a task slot. There's a separate pod called a triggerer, which has an optimization to make sure that these type of async functions don't use up a huge amount of resourcing for polling for something. So every 5 seconds, it's checking to see that it's there. And this can remain in the state until data gets updated. So if you were running this machine learning operations process in production, I would leave it in this state. So every time new data comes in, it would automatically trigger the process. If we go back and we rename the file now, options, rename object, save changes, and come back to here, you'll see that it's able to find it, and it will then move on to the next stage. So it's found it, it's now moved on to the next stages. So it's now running the fetch code and fetch data pods. So we have a look at the fetch data pod. It is creating a pod with this Kubernetes pod operator. And if we can go and have a look here, we can say Kubernetes get pods, and you'll see there's a pod running that's running fetch data. There is also these standard services. I built this Docker image. I use it for all of the things because it has all of the Python libraries I need when I'm actually doing those operations remotely. So when I'm connecting to that Kubernetes cluster, that's when I need TensorFlow. That's when I need Streamlit. So this is the Docker image that I'm going to use for this particular set of processes. So back into this file, you can see we're now over here. So we have started doing check sensor and the fetching of new data and new code. We can also see the nodes. Okay, get nodes. These are the nodes that we have. We only have one node at the moment. When we get to the next one, we specify container resources as an additional feature request. So this then says, passes to the Kubernetes daemon, I need NVIDIA GPU of 1. And also change the timeout because there isn't a node. So I need to wait for this node to arrive. So if we go back to here, we'll see it's on this process. It's waiting for this node to come up. So if we get the pods, the pod is in pending state. Get nodes, but we don't have a node yet. It takes about 3-4 minutes for a node to appear inside AWS in EU Central 1. So we'll leave that running and carry on with some of the other processes. But there is now a process that is requesting this. So you can actually, there is a mechanism, and in that EKS documentation, I talk about how to get logs in real time to see the scale up, scale down commands happening. But this is now going to then take and execute this line here, which is run the model training file with this as the path for where the data is stored, and this as the logical date. So we're using the logical date as a reference for the model. So we know that this was a training run and this was the logical date, which is understood by Airflow. If I ever need to go back and redo something, I can maintain my logical date. That model training code exists here in my include folder, in the code model training. And it is effectively taking that, that notebook file, this notebook file here. Did I actually go through it? In here, here's the notebook file that basically details all of the stuff. So there is a notebook that kind of talks you through step by step what the particular image classifier is doing. It's based on transfer learning. It's using MobileNet v2. There's a couple of things that are interesting in and of themselves with regards to how the machine learning model works, but not necessarily the scope for this discussion. But it is quite detailed. It kind of goes through data augmentation, other bits and pieces, and an extracted, summarized version of this is what we're running for the model training. So we're going through importing TensorFlow. Remember, it's running on a pod that is running remotely inside that GPU cluster. Do we have a node? Nodes? No, not yet. The things that I've added into this is here's where I start the MLflow tracking. So I pass the MLflow server. So you see at the start, I created those environment variables. I grab those environment variables from what I pass into the training, the start code. So here's the start code to say start with the MLflow server URL. This gets passed into that file. So this file is now running and it's going to execute, and it goes through this sort of straight model training process. Auto logging with MLflow is one of the reasons why I like MLflow. It does a lot of the thinking for me. I keep a history of the accuracy and the loss for this particular training run. And at the end, I save this into a Keras-based model on that stored persistent storage with the directory name being the name of the model. Let's have a look. Do we have a node? Yeah, we have a node. So the second node is coming up and it now says not ready, which means it's in a state about to get ready. If we get pods, you'll see that it's still pending, get nodes. That node is ready, get pods, still won't be ready, it will be pending, but it's actually now pulling the image. So if we go describe pod. So you can see it's busy pulling that image, and in a moment we'll start training. So we know that we will have this file saved when it completes. The next stage after this is, if we go back to here, this one, we now need to fetch the updated Streamlit code, which is also a Kubernetes pod operator. But for the Ray update, I've actually switched processes a little bit, and I actually switched to using this format here, which is the Tensorflow API based interface. And so the Airflow needs to know about Ray because it has to talk to the Ray server. So Ray allows me to connect to it on a remote port. It's also one of the reasons why I like Ray. It starts the serve interface from this, but I'm using Tensorflow API so I can keep my Python code inside my DAG. For me personally, I find this the easiest way to work. And one of the reasons why I'm quite excited about some of the roadmap items that will let us have more capable task options like Kubernetes-based tasks, or you get Docker-based tasks as well, where I can keep my Python code in there. It's easier for me to read and easier to debug because the Airflow interface will actually tell you exact line numbers that are breaking, as opposed to having to go and look in different files in different places. So Update Ray is a task that takes, if I go back to the code here, it takes this whole function and sends it to the Ray server as the new predictor function. So what we're doing is we're loading the trained model from the previous model training process because we know the logical date, and that is the identifier. And what this function does is it takes an image that is sent in a kind of like through a put process as a REST API request. And the data is base64 encoded PNG. It decodes it, converts it into a TensorFlow array, makes the prediction over here, and then sends back the result. This process updates the Ray server to use the latest version and checks, just basically restarts the process. The other thing that I needed to do is I need to work with this Taskflow-based API with basically the Python @task decorator with the traditional one. So we have to do a little bit of fancy footwork to get things to work for, like, say, passing in parameters and for getting the task dependency stuff right. But our starting point here is the current run. You can't use Ginger templating inside a taskflow decorator. It's not it's not meant to work like that. But you can just pass it in as as an argument. So I take the current run and I pass that current run into the function that I'm passing to Ray as a input into the actual function itself. So I call it, and Ray updated is the object that is then accessible by older Airflow objects. And this is the function call that actually does that process. So this is the function call that actually goes and updates the Ray infrastructure. Let's see how we're doing here on the pod. It is started. So if I go here, and go have a look at the log. When I jump to the end, we'll see that we should have something. Yep, so it's busy training. So it's currently running through the process, and this particular model is training at the moment. So yeah, updating the Ray, and we handed that through. So we actually passed the logical date then in through as an argument into the constructor for the taskflow based or the @task decorator. Then when we fetch the Streamlit code, this is the one thing that could definitely be improved. Because it's not maintained within the same cluster, I can't easily pass environment variables to Streamlit. I can't easily pass, I could have a backend database. MLflow has a SQLite database that it's talking to. I could technically write into that and then read from it from Streamlit. But I figured that the quickest way for me to do this was just use a quick sed command in Unix and then go and edit it in. So the file, the Streamlit code looks like this. And I just overwrite that with the variables, the information that I got out of the environment variables, and it just updates that file. So the file that's currently living in the ephemeral storage will have this information stored with it. And this is what this step does, is it copies the latest version of that file from GitHub and then makes those changes to that file. And Streamlit sees file changes, and as soon as it sees a file change, it restarts itself. So it's the easiest way for me to restart that process. Okay, and this creates the task dependency. So this is the map, and this is by using the Ray updated as an object that I can put into the task dependency with the right shift operator, allows me to build out this particular DAG. So the DAG over here, go back, close, this is the DAG, and it's running. Okay, so we have now built this process end to end, and in a moment you'll see that Airflow, in fact, it's there. So these are the two ones that are running. So these are the model training code that's currently updating Airflow. So it's still running. This was the first run. It's transfer learning. It does two processes, one with the base model weights locked, and then the second one, the base model weights get unlocked, and then you can actually train a little bit deeper. So it's a transfer learning mechanism. And it's based on the initial ImageNet weights, and we start doing 10 epochs with the X-ray images, and then we do another 15 where we're doing transfer learning onto that. So this is what is now being logged. Ray will update in a moment, and Streamlit will update in a moment as well. Now, from here, I want to push this into production because I can't run this on my local laptop. So production in the context of Astronomer means that I'm pushing it to the Astro cloud. There is an Airflow instance that has been spun up in the Astro cloud that I can push this to. And as long as I've maintained those same files inside it, the image is pushed from my local machine to a production, to the production infrastructure. And that instance will be able to connect through to my Kubernetes cluster. There is work that is being done right now from our product team to have the ability to move a ephemeral node group like this into the actual Astronomer control plane and into the same data plane where the Airflow instances run. So then instead of having to build a secondary cluster with auto-scaling GPU nodes, it can be just part of the standard Astronomer implementation. Then you don't have to do this complexity of the heavy lifting to be able to authenticate that Airflow process across. And that will make also certain tasks much easier to write and much easier to work with. So you'll have that is coming out in, I think, probably before end of August. It's called Worker Queues. And this is now something I can push into production. So if I go and have a look at my production instance, so this is our Astronomer cloud. I have a deployment here that I set up recently. So this is my cloud-based version of it. And if I click open my Airflow window, it will take me to my Airflow instance that's running there. And to go from how I have it on my local machine to what I push into the cloud is as simple as going here, saying astro deploy. It will then connect me through to that infrastructure, and it's now packaging up the Docker image and pushing it through to that deployment. So this deployment will run. So then I can disconnect my laptop and my machine learning model will continue running from there. So I want to talk a little bit about some of the tools that I used for this. And just, I think, to try and get make some sense of why I chose what I did. The first one is the orchestration. So obviously Airflow and Astronomer, there are alternatives, but they aren't really. So you could maybe use something, but since I'm in field engineering and responsible for sales, you're not allowed to because you're on this webinar and you have to use Airflow. But you could, there's Argo and Kubeflow, and there are other orchestration systems. Focus Flight is another one that's focused very, very specifically on machine learning. The complexity of this, and I'll talk about it in the next section, is Airflow does one thing that the rest of them don't, which is that it's not pure Kubernetes. So it's one of the reasons why I think it's actually a very, very good orchestration system for these type of things. The model training itself, I did with TensorFlow. I could have done this with PyTorch. Well, I say I could have done it. I could have followed a tutorial that does this on PyTorch and hacked my way at it. I just used TensorFlow because it's well documented and has lots of answers for things on Stack Overflow. And that's almost always actually one of my primary motivations for why I choose something, is I want to spend less time figuring out what doesn't work and how not to get around it. I want to get straight to things that actually do work. So Airflow is one of those, very well documented and has lots of community support. TensorFlow fits into a similar category. PyTorch is not bad. I'm not saying that these other ones are worse. This is just my personal approach to how I get these things done. For the experiment tracking, I used MLFlow, again, for similar reasons. In my experience with dealing with customers working in the machine learning space, MLflow gets a lot of traction for experiment tracking. There are others. So there is Weights and Biases, TensorBoard, DVC, ClearML, all very good, all do similar things. MLflow just has a very nice Pythonic way of doing things. And for serving, I used Ray. My initial build of this project, I didn't use Ray. And then I wanted to use Ray to see if I could do the training with Ray. And I found out that Ray Serve is very good. And Ray Serve is very good for two specific reasons. And so one of the reasons why I also like MLflow, and that is that I can test them without having to be deep into Kubernetes. So I can just run the service and test it and then slowly kind of build all of the infrastructure around it. And similarly with Ray, it's just run the Ray server, interact with it, and then you can start building the Kubernetes scaffolding that goes with it. Alternatives to this is BentoML, KF Serving, and Selden, both of things that as soon as I see Istio ingress requirements, I just really don't want to have to use them. So I go back to using something that I find just a little bit easier because it is more based around my background, which is kind of data science and Python rather than it is pure Kubernetes. And the application UI is based on Streamlit, which is basically, the Streamlit is effectively the same thing as Shiny, just for Python. But there are so many of these. There is a huge amount of tools that exist in this space. It's massive, and you can't always say that one is better than the next. I think that it's fit for purpose. I have my own criteria that I use for these types of deployments, but it is massive. Airflow can deal with almost everything because it sits outside. It's an abstraction layer away from the actual path of the data. It helps data move, but doesn't need to be aware of the data. So anything is possible for orchestration with Airflow. And I think that's one of the reasons why it makes it particularly useful. So I just want to sum up and have some final thoughts about this before we get into Q&A. The first thing is that the concept of a machine learning engineer or an MLOps engineer is, I think, mythical, because so the equation on the left is the loss function for gradient descent. And on the right was the service descriptor that I had to use for building MLflow. Knowing either of these subjects to a very, very competent depth is difficult. Knowing both, I think, is just a little bit too complicated. Like, you can either be very good at one or very good at the other. There are few people who are good at both. I'm not good at either, but I know enough about them to be able to get by. So this is something that I think is a requirement that people are going to have to work in teams and have to have a kind of central pivot point that they can both work with to be able to hand things across. And the one nice thing about the Astronomer CLI is it gives someone who's a data scientist an ability to just work on their local machines. You can actually build that whole Kubernetes environment on your local machine using the Docker Compose override functions that come with the Astro CLI. So you can build an MLflow server, have it deploy, you can have a Ray server, you can do all of those things just fully contained, including Airflow. And that can then be passed on to a team that can then build this out with the kind of full Kubernetes capabilities. So it acts as a conduit, a way of moving between those two locations. Then there's going to be things that I haven't included here. So what about hyperparameter optimization or AutoML? My model is surprisingly accurate. It's like at 98%, and I think that's because it is choosing a binary classifier to someone who has something in their lungs or someone who doesn't. And it's going to be very clear that those two images are different, so I don't need to go through that process. But if I were to get here, let's actually see how we're doing. It's this one, still running. I would add it into the training process. So you could build a grid search, or you could use something like Optuna or one of those processes that would do the optimization around it. Just remember that it takes more compute and takes more time. So if you have the time and money to optimize, and you have a model that can benefit from doing hyperparameter optimization or running it through some kind of AutoML process, then I think you definitely should. What about the all Kubernetes processes like Kubeflow and Argo? And I go back to my point about the fact that Airflow sits as an abstraction. Airflow can trigger any one of these processes. Airflow has a flight operator. Airflow can trigger Argo. Airflow can trigger Kubeflow. These Kubernetes-based pipelines do what they do extremely well. The complication comes in, and this is what I have experienced before. They like to contain the data into the image. So the data contains everything because that increases reproducibility. But in a big data context where you have big clusters of data or lots of Snowflake data or lots of data that's in Databricks, they don't easily contain it. So you need something that's still going to go and orchestrate and manage that process of extracting the aggregation, and Airflow can do that. So Airflow can replace components of Kubeflow, or it can augment Kubeflow, but Kubeflow can't do everything that Airflow does. So they can coexist, and I think it's important to understand the necessity of it. And one of the biggest complications with Kubeflow has always been, for me, debugging, because you have to get quite deep into the Kubernetes pod to find out why something's not working. So your first level of abstraction back when you're using Airflow and local development is it's much easier to debug, and then you can push it a little bit further in. So I think it's both the ability to deal with lots of different places or lots of different types of processes, and the ability to deal with very big data sets. So those are the two things that Airflow solves over and above what the kind of Kubernetes all the way processes do. We're not monitoring model drift because I don't have a real world example of someone actually testing this. So this would be something that we would be able to focus on what the models, how the model is performing, and then trigger the process. You could use Fiddler AI or Evidently at the end to actually track. And if you see significant drift, you can go back and trigger the whole training process using the API, because Airflow and Astro have APIs that let you do that. And then there's feature store. So we don't specifically need a feature store for this. And I'm on the fence about the actual benefit of feature stores. Feature stores, for me, I think fit into the category of, if you know you need one, you absolutely need one. If you don't think you need one, you probably don't. I think it gets to a point where, like, processing power means we can very quickly go through a piece of data and create a feature and then use that for model training. So that was the original Spark model, was you wouldn't store things in a feature store. You would just create a new data frame that is your feature store. So in this context, I'm busy working on another project that will use a feature store. For this one, that's not necessary. I could maybe have used it for something like some feature information and metadata, but I don't have that data. All I have is the image and the tag pneumonia or not. Alrighty, so thank you all. Thank you for your time. We've got, I think, 12 minutes left. So if there's any questions, anything that I can help you with, now would be a good time.
Jeff, that was great. Thanks for walking through all of that. What a cool example. A really interesting use case for Airflow. I haven't seen any questions come through in the Q&A. So everybody who's on with us now, you have 10 minutes or so of Jeff's time. So we'll give everybody a minute to throw anything in there if they have any.
Yeah, you can pop something in the chat or in the Q&A.
Yep. The chat is open as well. Maybe everybody on the call is like me and just wants to go play with the repo, try it themselves.
Yeah, so it's a good thing I renamed that S3 bucket back. So comment from Arun Kumar, thank you. Yep, thank you.
Got one question in the Q&A.
Yeah.
Got
It seems
that.
like Astro, Airflow, and Docker talks to Kubernetes via some kind of gateway. Is there a default setup for that? It's actually it uses the Python Kubernetes libraries, which in Docker I create when the Astro CLI creates a Docker network is one of the things it actually does for you. So it creates that pod has a virtual network and it has like a path so it can get through to the internet. It is going over the internet to my Kubernetes cluster. So there's nothing specific for this. The gateway itself is just an internet gateway. What makes it work is the description in the kubeconfig file tells that Python Kubernetes process where the main kind of Kubernetes daemon is running and how to authenticate against it. So those are the two things that the local Docker process has access to. So it is then able to go and connect to the Kubernetes cluster and EKS. So there's nothing specific from a gateway perspective on the local machine. It would be the same process that if I just ran kubectl get nodes, that same authentication mechanism is what the Astro interface uses.
Great question. All right. Well, if we don't have any other questions, everybody definitely check out the repo afterwards. If you want to play around with this example, we will be doing more content like this around ML and Airflow in the future. So really look forward to that, as well as got some great other events coming up to highlight, new providers and updates to open source Airflow. So be on the lookout for those, as well as the recording with slides and everything in your inboxes. So with that, I hope everybody has a great rest of your day, and we hope to see you next time.
Thank you all.
Thanks, everybody. Thanks, Jeff.